Close your eyes. Imagine a place where the sun is just another tiny, distant star. A place where the cold is so profound it seems to stop time itself. Out here, more than 15 billion miles from Earth, drifts a solitary wanderer, Voyager 1. It has left our solar system far behind, plunging deeper into the dark, uncharted waters of interstellar space. The environment around it hovers near absolute zero, the coldest temperature possible in physics. Yet this golden messenger from the 1970s has not frozen solid. It still hums with life. It still whispers its secrets to us across the cosmic ocean. How is this possible? How does a fragile machine survive the ultimate chill of the void? Today, we will drift alongside Voyager. We will uncover the warming secrets hidden within its metal heart, and we promise that by the end of this journey, you will feel the comforting warmth of human ingenuity. Take a deep breath. Let the silence of space surround you. We are about to begin. To understand this miracle of survival, we must first look back to a time when our journey began. The year was 1977. Humanity reached out to the stars, launching 2 identical probes into the sky. Their primary mission was to explore the giant, swirling worlds of Jupiter and Saturn. But their destiny was much grander than anyone could have imagined. Voyager 1 was launched carrying a golden record, a time capsule holding the sounds and greetings of Earth. It was originally designed to last just 5 years. But it kept going. It flew past the majestic gas giants. It crossed the termination shock. And finally, in the year 2012, it pierced the heliopause. This is the invisible boundary where the protective bubble of our sun finally ends. Voyager 1 became the first human-made object to enter the interstellar medium. Out here, the solar wind fades away completely. The comforting warmth of our sun is nothing more than a memory. The environment is harsh, empty, and incredibly cold, yet the probe's mechanical heart continues to beat. To understand why it hasn't turned into a block of ice, we must rethink everything we know about what cold actually means in the vacuum of space. But what does it actually mean to be cold in space? Let us clear away a common misconception. Many people picture space as an infinite freezer, expecting anything exposed to it to instantly turn into a solid block of ice, much like a liquid nitrogen experiment in a laboratory. However, this is a myth. Space itself does not have a temperature because temperature is a measure of the movement of particles. In the near-perfect vacuum of interstellar space, there are simply not enough particles to transfer heat away from an object quickly. Imagine stepping outside in winter without a coat. The cold air pulls the heat from your body. In space, there is no air to steal Voyager's warmth. So how does heat move in the cosmos? To understand this, we must look at the 3 ways heat travels: conduction, convection, and radiation. On Earth, we experience conduction when we touch a hot stove, and convection when warm air rises. But in the vacuum of space, conduction and convection are impossible. There is no physical matter surrounding the spacecraft to absorb its heat. The only way Voyager 1 can lose its heat is through thermal radiation, literally glowing its energy away in the form of invisible infrared light. Imagine a glowing ember in the center of a dark, empty room. It doesn't lose heat by touching the air, but by shining its warmth into the dark. This brings us to a fascinating realization. A vacuum is actually the perfect insulator. This might sound counterintuitive, but think of a thermos flask. A thermos keeps your coffee hot for hours precisely because it has a layer of vacuum trapped between its walls, preventing heat from escaping through conduction. Voyager 1 is essentially floating inside the ultimate cosmic thermos. Because it is surrounded by a vacuum, the heat it generates is incredibly difficult to lose. The challenge for engineers wasn't just keeping it warm, but initially making sure it didn't overheat while still near the sun. But what exactly is generating this life-saving heat so far from the sun? The answer lies in the beating heart of the spacecraft. It is called a radioisotope thermoelectric generator, or RTG for short. You can think of it as a nuclear battery. Deep inside this cylindrical device rests a precious glowing cargo, pellets of a radioactive isotope known as plutonium-238. As this plutonium naturally decays, it releases a tremendous amount of thermal energy. Imagine a rock that stays red hot for decades without ever needing to be set on fire. This silent, steady decay is the true source of Voyager's survival. The brilliance of the RTG lies in how it uses this glowing heat. The generator does not have any moving parts to break down in the deep freeze of space. Instead, it relies on a principle called the Seebeck effect. Special materials called thermocouples surround the hot plutonium. One side of the thermocouple faces the intense heat of the nuclear material, while the other side faces the cold of space. This dramatic difference in temperature magically forces electrons to flow, creating the electricity that powers the spacecraft's computers and radios. It is a quiet, continuous flow of life-giving energy. However, here is a secret of engineering. Thermocouples are actually quite inefficient. Only a small fraction, about 10%, of the heat generated by the plutonium is successfully converted into electricity. You might think this is a terrible design flaw, but in the frozen depths of interstellar space, this so-called inefficiency becomes Voyager's greatest strength. The remaining 90% of that nuclear energy is cast off as waste heat, and it is this very waste heat that floods the body of the spacecraft, acting as an eternal internal heater. Imagine a car engine that warms the cabin perfectly on a snowy night just by running. Let us take a closer look at the spacecraft's beautiful exterior. You have likely seen pictures of Voyager wrapped in what looks like golden foil. This is not just for show. It is an incredible piece of technology called multi-layer insulation, or MLI. It is an armor against the extreme temperature swings of the cosmos. The blankets are made of incredibly thin layers of kapton, coated with aluminum or gold. Imagine a high-tech version of those shiny emergency thermal blankets used by rescue workers. These golden layers serve a dual purpose, and they are essential for keeping the internal heat trapped. How exactly does this golden armor work? Remember that in space, heat can only escape as infrared radiation. When the internal components of Voyager generate heat, that thermal radiation tries to shine outward into the void, but as soon as it hits the inner layer of the golden blanket, it is reflected right back into the spacecraft. The multiple layers trap the radiation in a continuous bounce. It is like standing in a hall of mirrors, but instead of light, it is warmth that is being reflected endlessly. This delicate gold foil is the only thing standing between the delicate electronics and the endless cold. But thermal management is a delicate dance. While the main body needs to stay warm, the RTG itself, the nuclear heart, must not get too hot, or it could melt its own internal components. To prevent this, the exterior of the generator is actually painted entirely black. While the golden blankets reflect heat inward, the black paint is scientifically designed to be the perfect emitter. It absorbs the dangerous excess heat from the plutonium and radiates it safely away into the cold of space. Imagine wearing a heavy winter coat, but leaving your hands bare to release just enough heat to stay perfectly comfortable. As Voyager traveled away from the Sun, the temperature dynamics changed drastically. In the early days of its mission, when it was close to Earth and Jupiter, the spacecraft actually risked overheating from the Sun's harsh glare. To solve this, engineers installed clever devices called thermal louvers. Picture a set of window blinds attached to the side of the spacecraft. When the interior got too hot, these metallic blinds would automatically swing open, exposing a specialized radiator to the cold vacuum, allowing the excess heat to vent out into space. The magic of these thermal louvers is that they operate completely autonomously without any computer commands or electricity. They are controlled by bimetallic springs. As the temperature rises, the different metals in the spring expand at different rates, forcing the spring to twist and gently push the louvers open. As the spacecraft cools down, the spring contracts, pulling the blinds tightly shut to lock the heat back in. Imagine a mechanical flower that opens its petals to the sun when it is warm and closes them tightly to protect itself when the frost sets in. Deep inside the main bus of the spacecraft, under the protective golden blankets, the environment is surprisingly mild. Despite drifting through a region where the external temperature is hundreds of degrees below zero, the core computer systems and critical electronics of Voyager 1 sit comfortably around room temperature. It is a surreal thought. Billions of miles away, wrapped in silence, the heart of this machine feels much like the temperature of the room you might be sitting in right now. It is a tiny, localized bubble of Earth's warmth, sailing through the galactic ocean. Not all parts of Voyager are safely tucked inside the main thermal blanket. Some critical instruments and fuel lines must run along the long, spindly booms of the spacecraft, exposed directly to the harshness of space. If the fuel in these lines were to freeze, Voyager would lose its ability to steer, tumbling helplessly in the dark. To prevent this catastrophe, engineers wove a network of tiny electrical heaters along the pipes, much like a heated blanket you might use on a cold winter night. These little heaters draw a small amount of electricity to keep the vital fluids flowing. The fuel itself is a chemical called hydrazine. It is essential for firing the small thrusters that keep Voyager's main antenna pointed directly at Earth. Without this precise alignment, the spacecraft would go deaf and mute. But hydrazine has a dangerous weakness. It freezes at about 35 degrees Fahrenheit or 2 degrees Celsius, just above the freezing point of water. This means the thruster lines must be constantly monitored and warmed. Imagine trying to keep a fragile glass of water from freezing while standing in the middle of a devastating Antarctic blizzard. As the decades pass, a slow and inevitable challenge arises. The plutonium-238 inside the RTG has a half-life of 87.7 years. This means that every single year the nuclear material generates slightly less heat, and therefore slightly less electricity. The fiery heart of Voyager is slowly, beautifully fading. It is not a sudden failure, but a gentle, peaceful dimming, like a campfire slowly burning down to its final, glowing embers in the late hours of the night. With less heat and power, survival becomes a game of cosmic chess. To counteract this slow loss of power, the brilliant minds at NASA have had to make difficult decisions. They have begun a process of power management, carefully shutting down scientific instruments one by one to save electricity and preserve the remaining heat for the most critical systems. It is a poignant process. Imagine walking through a large, brightly lit mansion and slowly turning off the lights in room after room, gathering all your remaining warmth into a single, cozy living room. Voyager is shrinking its world to stay alive. One by one, the cameras that gave us the first close-ups of Jupiter and Saturn were powered down. The ultraviolet spectrometers were put to sleep. Each shutdown saves a precious few watts of power and redirects the electrical current to the vital heaters that keep the hydrazine from freezing. By sacrificing its senses, Voyager preserves its life. It is trading the ability to see and feel the interstellar medium for the ability to simply survive and whisper a steady heartbeat back to its creators on Earth. Even as it cools, Voyager is not completely alone in the dark. There is a faint, ancient warmth that touches it. It is the cosmic microwave background radiation, the afterglow of the Big Bang itself. This radiation fills every inch of the universe. However, it only provides a temperature of about 2.7 Kelvin, which is negative 270 degrees Celsius. It is not nearly enough to keep the spacecraft functioning, but it is a poetic reminder that even in the deepest, emptiest voids, the universe is never truly at absolute zero. A ghost of creation is always there. There is another fascinating scientific reality about the interstellar space Voyager now navigates. While the density of matter is incredibly low, the few particles of plasma that do exist out there can actually be incredibly hot, sometimes tens of thousands of degrees. This sounds contradictory, doesn't it? How can space be freezing yet the plasma is boiling hot? It all comes back to density. Imagine standing in a shower where the water is boiling hot, but only one tiny drop hits you every hour. You wouldn't feel the heat. Voyager sails through a hot plasma but feels only the bitter cold. As we ponder this, it is time to dispel another cinematic myth. In science fiction movies, when a ship loses power, frost instantly covers the windows and everything crystallizes in seconds. If Voyager were to suddenly lose all its internal heating tomorrow, it would not flash freeze. Because it is wrapped in vacuum insulation and golden blankets, it would actually take weeks or even months for the remaining internal heat to slowly radiate away into the void. It would be a slow, peaceful surrender to the cold, not a dramatic shattering of ice. The engineering of Voyager is a testament to human foresight. The men and women who built this machine in the 1970s had to predict how it would behave in an environment no human had ever experienced. They armed it with analog thermostats, simple metallic springs and glowing rocks, hoping it would be enough. And it was. The fact that its internal computers still operate today is like finding a perfectly preserved ticking pocket watch at the bottom of the Mariana Trench. It is a triumph of design over the most hostile environment imaginable. Right now, as you listen to this, Voyager 1 is still out there. It is quietly soaring through the darkness at over 38,000 miles per hour. Inside its golden shell, the last few heaters pulse rhythmically. The tape recorder spins, the radio transmitter beams a faint 15-watt signal back toward the pale blue dot it came from. The warmth inside is holding back the eternal winter of the galaxy. It is deeply comforting to know that in the vast, indifferent emptiness, a tiny spark of human warmth continues to endure. But we must also look to the future. What happens when the plutonium finally decays so much that it can no longer power the heaters? The day will eventually come, likely in the next decade, when Voyager will lose its ability to keep the hydrazine liquid. The thrusters will freeze, the antenna will drift away from Earth. The signal will finally, quietly, fade into static. When that happens, the spacecraft will enter its final phase. It will no longer be an active explorer, but a silent, frozen monument to human curiosity. Even when that day comes, Voyager will still not be truly dead. It will reach thermal equilibrium with the cosmos. Its metal body will cool until it matches the temperature of the cosmic background radiation, just a few degrees above absolute zero. At this temperature, the atoms within its structure will slow down to a near halt. It will become perfectly preserved in the deep freeze of space. Imagine a majestic ship encased in crystal-clear ice, untouched by rust, wind, or time, sailing endlessly across a dark sea. In its frozen state, Voyager will outlast almost everything we know. The golden record attached to its side, carrying the sounds of laughing children, classical music, and greetings in 55 languages, will remain pristine. In the frozen vacuum, there is no oxygen to tarnish the gold, no wind to erode the grooves. The cold that eventually claims the spacecraft's electrical life will become the very thing that immortalizes its physical form. The freezing of Voyager is not its destruction, but its transition into eternity. The story of Voyager's warmth is also a story of connection. Every time NASA engineers send a signal to the probe, it takes over 22 hours for the Lightspeed command to reach it, and another 22 hours to hear back. When they command a heater to turn on or an instrument to turn off, they are reaching across billions of miles to tend a fire they lit nearly half a century ago. Imagine a mother tucking in a child who is sleeping on the other side of the world. It is the longest distance act of caretaking in human history. This journey challenges our perception of what is fragile and what is strong. A delicate probe built with the computing power of an early digital watch wrapped in incredibly thin foil has survived longer than empires. It survived because it worked with the laws of nature rather than fighting them. By understanding the vacuum, by utilizing waste heat, and by trusting in the steady decay of atoms, we built a survivor. It teaches us that sometimes resilience is not about thick armor, but about smart, elegant design. As you let your mind wander into the deep space alongside Voyager, feel the profound peace of its journey. There is no turbulence, there is no weather. There is only a smooth, silent glide through the starlight. The darkness outside is absolute, but the warmth inside is steady. It is a perfect metaphor for the human spirit, small and fragile against the vastness of the universe, yet capable of carrying its own light and warmth into the farthest, most intimidating unknowns. Let the image of this golden spacecraft calm your thoughts. Think of the intense heat of the nuclear heart, safely contained, gently warming the cold metal bones of the ship. Think of the golden blankets reflecting the heat like a warm embrace. Out there, in the coldest place imaginable, human hands have placed a permanent pocket of warmth. The Voyager mission proves that even in the most isolating, freezing circumstances, warmth can be preserved if it is protected carefully. So, the next time you look up at the night sky and feel a chill in the air, remember Voyager 1. Remember that billions of miles past the stars you can see, a tiny piece of Earth is still staying warm. It hasn't frozen because it carries the fire of human ingenuity with it. It sails onward, a solitary glowing ember in the grand, beautiful dark, proving that the cold of the universe is no match for a well-built dream. Our journey alongside Voyager 1 comes to a gentle pause here. We have traveled through the coldest, darkest regions of the unknown, and we have learned that space is not just a frozen tomb, but a vast, insulating thermos. We have seen how a glowing heart of plutonium, carefully wrapped in golden blankets, keeps our cosmic messenger alive against all odds. Voyager 1 still flies, warm and awake, carrying the whispers of humanity into the eternal night. It stands as a profound testament to our curiosity, our engineering, and our refusal to fade quietly into the dark. Thank you for drifting through the cosmos with us today. May this journey bring you peace and a deep sense of wonder before you sleep. If you enjoyed this voyage, please subscribe, leave a like, and help our channel grow. We would love to hear from you. If you could send one short message into interstellar space on a golden record, what would it be? Tell us in the comments below. Until next time, keep looking up and let the stars bring you peace.